Okay, today I want to introduce another relatively new um, geovisualization technique. It's called LiDAR. And obviously, this is not a English word, right? It's an abbreviation of something. And its full name is called Light Detection and Ranging. Uh, According to the name, we know that this technique uses light to detect distance, right? Because it's ranging, okay? It's a remote sensing method, right? Uses light in the form of a pulsed laser to measure ranges or distance. 3D information about shape and surface characteristics can be detected by LiDAR. So you will ask, why is distance related to surface, to shape, and to mapping? Later, I will show you how they are connected. Okay. Because it's remote sensing, LiDAR is a type of remote sensing technology. I want to talk a little bit about the general process of remote sensing. There are two types of remote sensing: passive remote sensing and active remote sensing. The figure I'm showing right now is the general process of passive remote sensing. So here we have the sun. That's the sun, right? In passive remote sensing, sun is the source of energy. The energy here is specifically called electromagnetic radiation, okay, EMR. And here is the satellite, and the remote sensors, they are mounted on satellites, okay? So you can see that the energy is emitted by sun and reflected by the surface of the Earth. And the reflected energy can be what? Can be collected by remote sensors. So when the energy is traveling from sun to the surface of the Earth, it does not contain any information on the surface of the Earth. But when it is reflected by the surface of the Earth, it contains the information of the surface. For example, the reflectance of a tree or the reflectance of a roof, right? And then when this electromagnetic energy, which contains surface information, is collected by remote sensors, we can use images. We can use images taken by the sensors to what? To do analysis and to retrieve information about the ground, about the surface of the Earth. That's generally the process of passive remote sensing. Okay, and you can also say that the sensor here will also collect energy from the atmosphere, which is energy source 1. Energy source 2 is the one I mentioned before, right? It's the useful one. We still have energy source 3, which is energy emitted directly from the ground of the surface. I mean, the ground of the Earth or the surface of the Earth, right? We also have energy source 4, which is the energy emitted by the material under the surface of the Earth. So we have 4 energy sources, and the only useful one is energy source 2, which is sun, right? So you can say energy source 1 or energy 1 or energy 3 and 4. They are all useless. We don't want them in the when we process remote sensing data, we will try to eliminate 1, 3, 4, and only keep 2. Okay, that's passive remote sensing. We also have another type of remote sensing called active remote sensing. LiDAR is usually active remote sensing. Okay, and here we can see the process here. There is no sun in the sky because in active remote sensing, we do not need sun. The energy source is the sensor itself. The sensor will have specific device to emit energy, to shoot energy to the ground. And when this energy is or this EMR is reflected by objects on the surface of the earth, for example, this house or a tree, again, the reflected energy will have the information about this house, about this tree, and the reflected energy will be collected by the sensor, and then we will deal with the information, the energy collected by sensors, and then we retrieve the information about the house, about the tree. Okay, so yeah, passive remote sensing, active remote sensing, and you should know that LiDAR is a type of active remote sensing. Active remote sensing. Okay, for active remote sensing, there is another technology called radar. Radar is called radio detecting and ranging. LiDAR is laser detecting, light detecting and ranging. What's the difference between light and radio? We'll talk about that later. So radar transmits microwaves in pulses. Microwave is a type of electromagnetic energy with very long, not very long, relatively long wavelength, at least longer than visible light, than infrared light. I'll show you the spectrum later. And radar determines distance to objects. Okay, LiDAR transmits optical laser light impulses, also determines distance to objects. So radar or LiDAR, they have the same purpose, determines distance from sensor to objects. That's the same part. The different part is that radar uses microwaves. LiDAR uses optical laser light. So the difference is that microwaves, they have relatively longer wavelength. Optical laser light, it has relatively shorter wavelength. And here is the spectrum. Here is the spectrum. So when we are talking about EMR, electromagnetic radiation, we always use wavelength to categorize them. Okay, so here is the spectrum from left to right. The wavelength of EMR increases. On the left part, we have 0.0001 micrometer. Okay, so within this range, we have gamma rays and X-rays. And when the wavelength of EMR increases, we have ultraviolet, visible light, infrared, microwave, and TV and radio. So radar uses microwave and radio. So the EMR used by radar is somewhere here. So LiDAR, on the other hand, uses what? Uses visible and infrared EMR. And the visible EMR can also be called as optical EMR. Okay, so it means that LiDAR is using visible and infrared EMR. So the EMR used by LiDAR is somewhere here. Okay, and for a specific type of LiDAR, it's called terrestrial LiDAR. It's very high accuracy LiDAR. It is using near infrared EMR somewhere here. Okay, so you can say our eye system is relatively weak. We can only see visible light. That's the reason why it's called visible. It's somewhere between 0.4 to 0.7 micrometer. So visible light, this very narrow part of the spectrum, is the spectrum our eye system, human eye system, can use to perceive our surrounding environment. Okay, so LiDAR here, radar here. Okay, so that's the difference. I mean, based on this difference, radar and LiDAR, they have their pros and cons. For example, radar, it penetrates clouds, long operating distance, cannot detect small objects, cannot provide precise images. Okay, penetrates clouds, long operating distance. This is the advantage of radar. Because the wavelength of microwave is pretty long, it can penetrate clouds. And because the energy of a radar sensor is high, radar can be mounted on planes or satellites, long operating distance. But meanwhile, it cannot detect very small objects, for example, a tree. Especially if the tree is not very big, it's pretty hard to detect. And cannot provide precise images. In other words, the spatial resolution of radar images is relatively low. You cannot differentiate a car from another car in a radar image, because a car for a satellite sensor is, a car for a radar satellite sensor is just too small. But on the other hand, LiDAR, it can detect small objects, produce accurate 3D images. Here, specifically, these 3D images, they are for what? They are for the surface of the Earth, because LiDAR can provide a very accurate elevation data, okay? But LiDAR cannot work in bad weather. It cannot penetrate clouds because it is using optical EMR. When you are looking into the sky and there is a cloud, can you see something? Blocked by the cloud? No, you can't, because our eyes they're using visible light. It's same for LiDAR system. Although some LiDAR systems they use near infrared, but a lot of them they are just using visible light. So if your eyes cannot see something, then LiDAR cannot see that thing. Okay, and it cannot work with pretty long distance, short working distance, usually 500 to 2,000 meters, which means that LiDAR sensors, they are usually mounted on cars, on drones, or on planes, but not usually for satellites. There are LiDAR systems mounted on satellites, but very rare. And very expensive devices. A LiDAR system is not something you can buy on Amazon. Maybe you can buy it on Amazon, but they're very expensive, especially for those very accurate LiDAR sensors. So you can see here, we have pros, we have cons for a radar and LiDAR. That's the reason why they both exist, because depending on your specific application, depending on your funding or on your purpose, most importantly, depending on your purpose, you should choose different technologies, but they both detect distance. And history of LiDAR. At the very beginning, laser ranging was developed in 1960s for meteorology applications, because it cannot penetrate clouds, so they can be used to detect clouds, right? If you shoot a signal to the sky and it is reflected, then you know there is a cloud, right? If it is not reflected, then you know it's clean sky. And the LiDAR terrain mapping began in the 1970s. So it's relatively new, not very new. And early LiDAR systems were used for bathymetry, and the mapping accuracy was limited by the poor georeferencing, because GPS was not a thing back then. But when GPS appeared, and also another equipment is called IMU, inertial measurement unit. Both of them together, GPS and IMU together greatly improved accuracy of LiDAR system. GPS is for the positioning of your sensor in the sky or on the ground. IMU is something else, can detect the gesture of your sensor. What is gesture? What's the observation angle of the sensor? Where is the sensor looking at right now? They are all about the gesture of sensor, the angle of sensor. Okay, IMU can accurately detect that. And there are different types of LiDAR depending on your purposes, right? There are aerial LiDAR systems, right, on drones, on airplanes for highly detailed local elevation and distance data. So usually, if you're interested in urban ecology, for example, the distribution of grass, of trees in urban areas, precise agriculture, you want to know the health condition of your plants, right? You can use LiDAR. And archaeology research, etc. A terrestrial LiDAR, that's another type of LiDAR, a stationary or mobile for extremely high detail or accuracy applications. Today, Tesla and a lot of other big companies, they're trying on electronic cars and also automatic driving systems. The most important thing, one of the most important things for automatic driving is distance detecting. Why? Because when a car is running at high speed, if there is a driver, that driver should be very careful with the surrounding environment to make sure that the car is not running into something, right? Or some people. But if the computer is driving the car, what's the eye of the computer? LiDAR. LiDAR can do that. If you check the surrounding of a high-end car with automatic driving system, you will see that there are a lot of distance sensors surrounding the car, mounted on the car. Some of them, if the car is expensive enough, these sensors could be LiDAR. They are detecting the distance from the car to the surrounding environment nonstop to make sure that there is no pedestrians or no trees or curbs, to make sure that they are not too close to the car. Okay, so distance detecting is important to automatic driving. Okay, and both of them, no matter aerial or terrestrial, both can be combined with digital imagery for realistic 3D models. So why here? Why is distance connected to 3D models? Because when you're, for example, you're standing in the middle of a room, and here, if you want to create a model of the room based on the information you have, based on the information of your position in this room, what do you need to measure? You need to measure the distance between you and every corner of this room. If you have a complete data set of distance between you and every corner of the room, you know the shape and the size of the room, correct? And if you know that, you can easily, because you have known the shape and also the size of the room, then you can create this model. It's the same thing for LiDAR. If a LiDAR sensor has covered a huge area on the ground, it will have accurate information about the elevation at different points within this area. And if you connect all those points, you have a very accurate surface model for that area, correct? If you want to have a very accurate, extremely accurate surface for that area, you just need to make sure that there are as many points as possible, right? And each point has a specific elevation value detected by LiDAR. Okay, later I will explain this in detail with figures, but you should know that distance detecting is closely related to 3D surface creating or 3D environment creating. Okay. And we also have satellite LiDAR. Like I said before, it's not very common, but there are. An example would be glass. It's called geoscience laser altimeter system for large-scale studies with less details. If you mount LiDAR on a satellite, you cannot expect the accuracy too much. Okay, but if you put it on a drone or a plane, it's much better. It's much better. But if you want the highest accuracy, it should be what? Should be on the ground, mounted on a car or something on the ground, right? To measure, to collect information. And also based on the purpose, based on the research object, a LiDAR could be topographic or bathymetric. If it is topographic, it uses a near-infrared, usually a LiDAR system for topographic mapping, uses a near-infrared laser to map the land. This is the most commonly used type of LiDAR. We want to map the surface of the Earth, of a specific area. Bathymetric LiDAR systems use water-penetrating blue-green light to measure seafloor and riverbed elevations. Again, it's for mapping. But since there is water, we want to penetrate the water and to detect the information of what? Of seafloor and riverbed. Okay. So purpose of LiDAR systems: examine natural and man-made environments with accuracy, precision, and flexibility. You can mount it on a car, on a plane, on a drone, or even on a satellite. That's flexibility, right? They have different spatial and spectral resolution, right? Output examples produce more accurate shoreline maps, making maps, and make DEMs. DEM, the full name is Digital Elevation Models. A DEM model is basically a bunch of points. Each point has a specific value for the elevation of that position, of that location in the real world. If the number of points is large enough, you can use these points to create a very accurate surface of the Earth, right? So DEM is pretty important. It's in GIS, okay, this concept. And assist in emergency response operations if there is earthquake, if there is flood. LiDAR systems can be used to retrieve information firsthand. Okay, you can simply mount it on a plane and let the plane fly over the area affected by disasters. It's very convenient. I would say it's expensive, but in emergency, it's very necessary because decision makers, policy makers, they need the first-hand accurate information for decisions, right? And here are some examples of fields of application. I'm not going to read them directly, but you should generally have an impression about all those fields. LiDAR can work. LiDAR can work. And actually, in general, remember this: if you need distance data, as long as you need distance data, LiDAR can work. LiDAR can work. Here, I want to introduce the operational theory of LiDAR. So here we have a plane flying over this rural area. Okay, we have a barn here. We have trees. We have trees, and the surface is not flat. Okay, a pulse of flight is emitted, and the precise time is recorded. Here, time is pretty important. You need very accurate time recording for a LiDAR system to work. I will tell you why later, but now remember this. So we have a lot of dash lines here, right? Each dash line, you can consider it as a what? As a pulse of light. The reflection of the pulse is detected and the precise time is also recorded. So when a specific energy pulse is emitted by the sensor, it will arrive at the ground and reflected by the object at this specific point, at this specific location. And the reflected energy will be collected by a laser scanner or the sensor again. Okay, and both shooting time and the time receiving the energy will be recorded. And given the constant speed of light, the delay or the difference between shooting time and receiving time can be converted into a slant range distance, okay? The longer the delay time, the longer distance the signal travel, right? Due to this, based on this relationship, we can convert time to distance. Knowing the position and orientation of the sensor, the XYZ coordinates of the relative point can be calculated. Okay, this is for the positioning of this point of this object who reflected the energy. In order to find out that, we need XYZ. And XYZ can be decided by the position of the sensor and orientation of the sensor. Remember GIS and IMU, GPS and IMU. GPS is here for the position of the sensor. Even the plane is flying pretty quick, pretty fast. As long as your GPS is accurate enough, position of the sensor can be recorded. Orientation can be what? Can be detected by IMU. Okay. So here is the operational theory of LiDAR. Shooting energy reflected by the surface and receiving the energy, receiving the reflected energy, and calculate the difference of time between shooting and receiving, right? And we can convert that time to distance. I'll give you the formula later. And then meanwhile, you need to know the position of the plane, and or you can say the position of sensor, right? Position of sensor and orientation of the sensor to what? To find out, the specific location and the information, the position, location information of the ground object who reflected the energy. Okay, I think that's too much for a video clip. I'll just stop here and continue later. Thank you.